So recall that we have this Aztec dimer, but we could also think of it as this dimer configuration here. So I also showed some pictures of this height function, this random surface here. And let me be a little more precise now what I really mean by this height function and how it's related actually to the dimers or to the tiles here. So there are some specific rules which tells you what to do. So I put the height 0 here. And if I cross like a dimer like this with a white vertex to the right, then I go up by 3. If I cross like this where there is no dimer and I have a white vertex to the left, I go up by 1. But if the white vertex is to the right, I go down by 1. And similarly, of course, if I cross the dimer in the other directions, I interchange it, then I have to go down by -3. Right? So the steps are always plus -1 and plus -3, depending on whether you don't or do cross the dimer. Right? So this is what I've written here. So if you start here, you can just go through and you see that these definitions are consistent when you go around a point like this. So in this way, you see, we can associate with this random tiling or this dimer configuration these heights which sit on the faces of this graph. And of course, you can go the other way around, that if you have this type of height function which satisfies certain restrictions, and due to this, you can go back and recover the tiling. So the two periodic Aztec dimer that I briefly mentioned and showed you some picture of, this is a different choice of weights now. So in the following way, that all the edges that go around this square here, they all have weight 1. All the edges that are around this square have weight A, and then 1 and so on. You see, in this way, so this would have weight A, this would have weight 1, and so on. So in this way, I get this sort of two periodic structure in the weights then. So this is a different choice of weight than we had for the sort of standard Aztec diamond that I was talking about in the previous talk. So so of course, I mean, the definition here of the height has nothing to do with the weights. I mean, given any dimer configuration, I have this surface, right? Discrete surface. So if you do a simulation then for this two periodic tiling. So here's a sample from this. So you still have these sort of flat pieces here. And you have this which is sort of curved here. And here is this kind of edge we were discussing again. If you look, you can see it sort of looks flat here, but not completely flat. So maybe it's a little clearer in this picture here. So here is a flat piece. Here you have these sort of curves that we saw in the previous. So here we should expect to see this airy process, yeah, right? But here you hit something which looks flat but has some sort of dents in it. And there seems to be some kind of boundary here, but it's less clear what it is than this one, right? Here, what is the microscopic boundary, so to say, is very clear. I go from this completely flat and I see the first dislocation, something different, right? Whereas here, it's much less clear when do I go from this sort of curved things and these things that look like long paths to this sort of disordered part here. This is not so obvious, right? You can also imagine that if I take a really large one, there is a limiting shape here, right? This would be the macroscopic limit shape of this surface. And this is a solution to a certain variational problem. So this is a sort of a typical situation. I mean, the limit shapes themselves are also very interesting. I mean, there is to understand the macroscopic shapes. I mean, they could be described by some variational problem or some PDE or something like that. Right? I mean, to compute the macroscopic limit shape is generally a hard problem. So, and of course, as I emphasized in the last talk, I mean, we really need to know to some extent the macroscopic shape also, right? Because the geometry there will decide what type of limiting behavior I can see and where I can see it. This is similar to random matrix theory. I mean, I have to know the global distribution of the eigenvalues so that I know, am I in the bulk or at the edge or outside the spectrum, right? So I need some information about the global structure also. So I will not sort of, so this is an interesting problem in itself, this variational problem. So it has this form. I have some surface tension depending on the details of the model here. And I have sort of a gradient variational problem. So the gradient of the height function and evaluate this surface tension there, I integrate over sort of the region that I have, and I take the infimum over all these candidate height functions with a bound of the Lipschitz constant here. I mean, because, and this bound are sort of these limiting slopes that correspond to these flat pieces. So I hit these upper constraints then, upper and lower constraints at these sort of frozen parts then. So the limit shape itself is sort of like a free boundary here, I mean, which is not a priori determined, right? It depends on the choice of the boundary condition or which region I have here. Right? You could see if you go back here, the heights along the boundary are deterministic here, right? So the shape here of the Aztec diamond determines what the height function is at the boundary. Right? So this is sort of given. But what happens inside, of course, depends on the particular tiling here, or the particular dimer covering I have. So there is an interesting theory around the sort of limit shape here. So this is another representation then of these two periodic Aztec diamond. Here you see quite clearly that this flat part in the center of the height function. Here corresponds to this curved part. Here are these sort of completely flat pieces. And you can see that there are these sort of, it seems to be like these curves here. And this curve here is quite well defined, and this also looks quite clear. But if you look locally here, it's not so clear what is actually this curve here. So the interest in this model is that we have this kind of boundary, which is similar to what we saw before, but we also have this boundary here to this not completely flat region here. So actually, there are three types of faces. Or if you would look at this microscopically, there are so-called Gibbs measures, which describes the local structure of the tilings or these dimer models here. And they come in three types, which are called gas, liquid, and solid here. So it's nothing to do with gas, liquid, and solid, which we see around us, but it's just names here, right? And Kenyon and Kunkov, they have characterized all the possible Gibbs measure that you can get in this type of models, and they come in three types then, which are called solid, liquid, and gas. And you can describe them by sort of limiting infinite tuplets, Castellane matrices, which sort of describe the infinite tiling of the whole plane with this type of faces then. So there are sort of solid type inverse, infinite inverse Castellane matrix, liquid types, and gas type then. And you can see the difference between these types of faces in how the dimers or dominos decorrelate. So in the liquid phase, they are relatively strongly correlated. I mean, the correlation between different dimers decay as 1 over distance squared. Whereas in this gas phase that we had in the middle here, they decay exponentially. So this is much more disordered, which you somehow could see in the picture also, right? So you see here in the liquid region, we have this sort of connected long-range structure, whereas here it's much more local. Here in the solid, it's sort of completely correlated, right? So as I said, in this model, we have two types of boundaries. We have boundaries between the gas and the liquid region and between the liquid and the solid region. So if you believe this universality And remember what I said in the last talk, I mean, certainly here at this boundary, we should see just the area process again. This is what you would expect. But what happens here? I mean, here the boundary is not so clear, but is it still true that we have some kind of area process in the limit there? So this is an example, you could say, of a universality question now. And how does this result extend to this new type of boundary? I was arguing that these type of limits that I've described are universal in some sense. So do they apply here? So this is not sort of a broad universality question. It's going to a somewhat different type of models with a different structure and asking, do I still see the same limit here? So this is a sort of a step towards universality to see how far can we, in different concrete examples, extend this theory. Yeah.
So if you had a different model kind of like this and you saw the same kernel, then you would say, like at the boundary, you say you find the boundary, the kernel for the boundary between gas and liquid, and you got it, and then you saw it, and it's sort of a different model, and you got the same kernel, then you would say,
yeah, I mean, you would expect, just as we would expect it to be the same when you have this kind of going from a solid to a liquid phase, boundary between this should always be given by this area process within a reasonable. And here, presumably, if we can understand it in this specific model, this would be the natural conjecture what would happen in all different that.
the width of this liquid phase, as you grow,
Yes.
does it stay?
No, this is always this is sort of the macroscopic picture. So the size here is always of order n if n is the size here. So this is a macroscopic shape. So we always have the size here. By varying this parameter a, you can change the relative size. So by taking a smaller, this gas part would expand and the liquid would contract, right? But so you can vary it in this way, but it's always for a fixed A has a macroscopic size. So what can we say about the edge fluctuations in this, at this liquid boundary? And how should we even define it, as I said? Here's another, it is much less clear what's happening here at this boundary than what you see here. So we need some description of, and again, just as in the previous talk, we need something to really compute with, right? We're not at the, I mean, this, as I said, it's universality in the sense that I try to extend the result we know at the other boundary to this boundary. But it's, I mean, I want to prove it using some explicit formula to actually compute things. So I'm still looking for some exactly solvable model here where I can actually compute things. So what we saw in the previous talk from this general Castellane theory is that the diamonds, they always form a determinant Lapointe process. I know it's a determinant Lapointe process. So in some sense, I only have to compute the inverse Castellane matrix, and then and work with it. But this, of course, is not an obvious problem at all, as I said. How do you actually compute the inverse? So it's not a sure process. I cannot, in any obvious way at least, relate it to that. I mean, because this is because I lost this translation invariance due to this two periodicity. So the non-intersecting paths we have not been able to use. All of this could be possible, actually, also. I mean, that's an interesting problem. So let me sort of say what we have been doing here on this model then. So you can introduce some coordinate system just in this graph here, right? So just to know what points we're talking about in this graph. And then you can let, it should be a Km here, be the Castellane matrix for a size n equals to 4m two periodic Aztec diamond. So it's convenient to have size 4m, I mean, in the formulas. And then Sunil Chita and Ben Young, they actually were able to find a generating function for the inverse of this Castellane matrix in a rather remarkable computation So by this I mean that you take this inverse, so x1, x2 is some white vertex, right? So you go through all these white vertices here, and you go through all the black vertices, right? And you take the inverse Castellane matrix, which is sort of white-black, right? And you put some parameters in the generating function here. You think of them as complex numbers, right? And you sum this up. It's a finite sum. It's some polynomial in 4, or Laurent polynomial in 4 variables, right? Or really a polynomial here, right? So, and they get an expression from this, but it's extremely complex. It takes 2 pages to write down. So it's not an easy thing. So even though you have this formula, it's not really clear what to do with it. So, but after quite a lot of work, we've actually had to use some computer algebra also for just working with these things. I mean, it's elementary things, but just rather long formula, right? So which Sunil Chita was very good at to work with. We could actually get a much easier formula, extract something useful out of this complicated generating function. And it has this form that we have sort of an infinite gas part here. So this is the Castellane matrix for sort of an infinite gas phase. And then there are 4 other terms here in this formula also. And they have, again, a double contour integral form, which is sort of the kind of thing you would like. You want some contour integral or something like that, which you can use for asymptotics. Right? And the details are not so important. This is some complicated expression. Epsilon 1 and epsilon 2 depends on the parities here of x and the coordinates here. But this is not it doesn't depend on m, so it doesn't come into the asymptotics. These do come in the asymptotics. So they have some explicit formula like this here. So g omega is this. You can see it's a solution to some quadratic equation, but it's not a rational function anymore. In all the other models, you typically have rational functions here in this thing, in the Schur process, or exponential functions. So here it's something more complicated, but still it's a relatively reasonable thing to work with. Right? So once you have this, you can start to do asymptotics. So, for example, just to indicate something, if we go back to this picture here, for the Aztec diamonds, one periodic standard Aztec, you got this ellipse or a circle, right? So you could ask, what is this algebraic curve? Or it is an algebraic curve. This was known and had been computed in some cases by Kenyon and Okunkov. But you can actually, this is a degree 8 algebraic curve, actually, and you can see how you can get it out of this formula, just to illustrate something about asymptotics. So what do you do when you have a typical saddle point argument, you want to have something like this, and then the critical points of this function f of c here is what determines the asymptotics of this, right? So this is what's been done here. You take the log, you write it as e, you have this h here, and you write it in exponential form instead, like this. And then you have this thing here, where xi1 and xi2 are the rescaled coordinates. Right? So you have this shape here, and I define sort of macroscopic coordinate xi1 and xi2 like this here. And then we know from previous experience that sort of area functions appear at these boundaries, right? And area functions in this type of saddle point arguments, if you want to have an area asymptotics here, you would be looking for points where both the first and the second derivatives are 0. This is sort of a known recipe. So if you do this here, you get this equation. And if I eliminate omega c here, I get an equation for xi1 and xi2. And this becomes an 8th degree equation with 2 real components, which are these things here. So this is how you get these limiting curves here. So they fall out of this formula quite immediately, what the limit shape is. I mean, we haven't proved that it actually converges to this, but you can see what the limit should be. But to really understand the behavior at the boundary, you have to do a more precise analysis there. I mean, I didn't discuss this in the previous talk, what you actually do, and I will not do the asymptotic analysis, but it's based on this type of saddle point argument. So it turns out that it's easiest to zoom in along this diagonal. So I zoom in at this point, at this liquid-gas boundary. So I do this, just as we saw previously, I do these suitable rescalings again, right? So in the direction 1, 1, which is sort of orthogonal to the curve here, I have the exponent 1/3 again, right? So and tangentially here, I have the exponent 2/3. And rho would decide then the position. It comes from this macroscopic. I know from the previous argument what this point is. I mean, right? So this decides this rho. So I put this into the formula and try and work out the asymptotics. And what you get is that you still have this gas part, and then you get a correction to this gas part, so this is order 1, right? And this goes to 0, but contains an area part here, which is related to it's basically the extended area kernel that we saw previously, or part of it. So this indicates now very strongly, of course, that what you see here is, again, some kind of area process here. Right? But a difficulty here is that the dominant thing, you really only see a gas. This is a smaller, so if m goes to infinity, this goes to 0, and I just see a gas, right? But of course, this is what you would expect also. I mean, we have this, if you look at this picture around, we have this thing here. I have these sort of curves here. But all around there, you just see gas, right? So let's go back to the picture, maybe it's clear. I mean, you see, if I zoom in here, I basically see a gas phase there. And now and then, I seem to see some long-range structure. And this long-range structure then must somehow be coming then from this thing, right? But the typical distance between these long-range structures is actually m to the 1/3. So if I'm standing at a fixed position, I'm just see gas around me. Now and then I could happen to be at this line, right? But this probability of being just at one of these lines goes to 0, and this is what you see here. So that means that to separate these two effects is now very difficult, because this is the dominant part. It lives at one scale, and this lives at a much smaller scale somehow. So if I had been now at the other boundary, at this sort of liquid-solid boundary, then I would only be seeing this part. And this would sort of be trivial. This is sort of fixed, right, in some sense. I could easily sort of subtract it away, but here I cannot really just take this away, because this still represents this gas randomness somehow. So this is why this problem here at this boundary is considerably more difficult than at the other type of boundary.
Since it's a smaller effect, I guess it is much harder to see it.
It's much harder to see. It's harder. I will come to a result in a moment here, which tells you something about it. So how do we actually see this at all? I mean, so you can see that these curves that seem to be here in this, they are actually related to height changes here now. So if I go here, I mean, going up here is you basically related to these kind of curves that you see. But I mean, there are all these, when you see this gas phase, it's only not completely flat either, right? So there is these small steps also, which also represent height changes. And somehow I have to separate these sort of long-range height changes from these local small things here. Right? So long-distance effects due to this large scale should be due to this, right? And But basically, these small things should be more or less independent, right? Remember that I said that the gas phase correlations actually decay exponentially, right? So if you believe that it's basically like some kind of gas phase plus something else, which is not really the case, right? Because they are intertwined somehow. But you still could believe that if I somehow could average out these gas effects. Right? So this is the idea. We look at height differences, but try to average out the gas effects. So we try to define not a point process now, but a random measure instead, in the following way. So maybe I should actually describe this. So I pick some deterministic intervals. And so I have, in the picture, you sort of see these long scale things, right? And then, but there are also these gas things, which are sort of some small changes also here, right? And then I take some interval going across here, sort of the size of m to the 1/3, or n size of the Aztec diamond to the 1/3 then. But I take several of these sort of, I take copies of these in parallel, right? Where this distance is sufficiently large, say log m squared here. So this means that these small features that you would also see here should be sort of, which affects the height here, should be more or less independent on these. So I can take the height difference between these 2 points here, and these 2 points, and these 2 points, and then take the average of this. Hopefully this should average out these small scale fluctuations. And what I should be counting them in the end are these long paths. So because these long paths represent sort of going up one step. But most of the height fluctuations are actually due to this gas thing. Right? So this is the idea. I take these sort of limiting, I put copies of these things. So here are these curves going through that I draw on the board. I take height differences that I said along these, and I take the average of these. This defines now a random measure. So if we believe again that this should converge to this area kernel process that we saw in the previous talk, then this random measure should converge to a point process given by the area kernel. And the result that we got this year is that this is actually true. This does converge weakly to the area point process, which means that I have a determinantal process given by this area kernel. I can do this in different places also and get this extended area kernel. So in some sense, we see that we are seeing the same type of boundary behavior here as at the liquid-solid boundary. We don't really have the convergence of a random curve that I had in the previous case, right? But so it's a little weaker. We hope to be able to prove that also, but this is a little harder. So this is then a kind of universality result in the sense that we, at a rather different situation, we do get the same limit again. This is a little different than, the proof here is different than the typical arguments you've seen, because you just have this Fredholm determinant, you prove that the kernel converges, the whole Fredholm determinant converges, and you're done. But this doesn't really work here, because we have to separate this big effect from this one. Somehow this has to cancel out. So here it involves a rather subtle cancellation between different parts. So we actually use a cumulant type expansion. So you take the log of this Fredholm determinant, you have a cumulant expansion, and you work with that instead. So the argument has a different structure than the standard ones for those of you who may have seen them in, say, random matrix theories, other models. So this is a different type of limit theorem in that way. So as I said, you could see this as one step towards universality in the sense that we have another model which shows the same limiting behavior. But of course, there is a much wider universality question then, right? So can we prove within some large class of models? Say you take polygonal shapes with holes and different things like in a hexagonal type of lattice, right, and you tile it by rhombi, could you prove that the limits that I showed you in the previous talk are all the limits you can get? So you would have some limit shape which you could determine in principle, at least from this variational problem. You zoom in a certain geometric situation, then the conjecture would be then that you do get one of these limits that we see, that I indicated to you. So this is the universality problem, and this is known to some extent in some rather small subclasses of model, but it's certainly open in a broader sense. And of course, if you go to other classes of model like random growth, it's even more open. Six-vertex model, this Aztec diamond is, I won't define this. I mean, this is a special class of another model, special case of a model called the six-vertex model. And you can, if you simulate this, you can see similar pictures to the one I've shown you. And you could expect other limit results. But then we are in this situation that you're sort of going beyond determinantal. We don't really know how to write down things directly in terms of a determinantal process in this case. I mean, so this is more difficult. It connects with also with recent work on this, as I mentioned, on this going beyond determinantal processes. So as I've indicated, there is a connection to random matrix theory in the sense that we get similar distribution. There, due to work of Yao, Erdős, Klein, Tao Wu, and others, there has been a lot of progress on proving universality in Wigner matrices, for example, and variations of Wigner matrices. But the difference there is that you have many more tools. I mean, you have matrix, you have resolvents, you have perturbation theory, you have other methods which you can sort of work with. And this is sort of what's lacking in this type of models, that we say that I change some model and perturb it. I didn't define this. This is an example of a last passage percolation model. I connect points 1, 1, and mn with some random walk type path. I pick up independent random variables at each of these points and take the maximum over all paths here. So if these are geometrically distributed, this is related again to these Schur processes that I was talking about. You can compute things, you get the traceability distribution, you know. But say that I change this to some other distribution, then we don't know anything. So this would be a sort of an analogous problem to the Wigner matrix problem, right? We change from some special structure like GUE matrices to more general matrices, right? But here, I mean, there is no perturbation theory, there is no resolvence, there is no structure like this that we can use. So this, I think, it's a challenging, interesting problem where new ideas are really needed. I mean, so how to approach it. Let me just mention at the end here also that I indicated we had this random surface, right? And you can, of course, also ask for the fluctuations of the surface itself. I mean, so you subtract the limiting surface from the random surface and look at how this fluctuates. This is known to converge in certain cases to the Gaussian free field. And there is a general conjecture here also, kind of universality conjecture, that the fluctuations of this surface should always be given by the Gaussian free field. As far as I know, there is really no connection with this and this type of edge behavior that I've been talking about. I mean, so because this Gaussian free field doesn't really see the edge somehow. I mean, so there is these two areas of fluctuations in this model are quite disjoint so far. I mean, the methods, the ideas the results for the Gaussian free field is sort of one side of the story, and these edge fluctuations another. I mean, so, and they, of course, there is no clear relation between them either. But this is another type of universality question, is to prove this Gaussian free field for the fluctuations of the random surface itself. So, okay, thank you for listening. There.
That point there.
Yeah.
What about it?
Yeah, we haven't looked at that. It's not clear, actually. It could be, presumably it would be related to some Pearcey thing, but it's a little less clear. I mean, you could think that it should be cusp area, as I mentioned also, but this is not, we don't know. I mean, presumably I would think it's some kind of Pearcey thing there. It's a little, the formulas, even though they are explicit, it's not so easy to work with them in all cases. We haven't really figured that out. So. But this you can probably do, I mean, but we just haven't done it.